In this lesson, we're going to take a look at weight and the normal force. Now, those are two forces that act, we generally think of in the vertical direction, although the normal force doesn't have to. So let's start by addressing the concept of weight. We're all familiar with weight. We know the definition of weight, right? This is the force due to gravity, right? Because we're in a gravitational field, a force is exerted on us. And it is actually very, very closely related to mass. It's not mass. Mass does not measure weight. Weight does not measure mass. But there is a direct relationship between weight and mass, and that's due to gravity, right? Because gravity acts on all things with mass. And the more massive the objects are, the stronger that force is. So more mass creates stronger gravity. Okay. Now, we put this together and it's easy to see why we confuse mass with weight, because more massive objects also have more weight. But they are different because mass does not measure a force. Mass measures an amount of matter. It tells me how much stuff is present, how many atoms are in an object. It does not tell me how strong a gravitational pull will be. And in fact, the gravitational pull depends on whatever planet we happen to be on, or whatever mass is creating the gravitational field. On Earth, we think of Earth as creating the gravitational field. We have a certain weight. If we move to a different planet or to the moon, then the different gravitational field means we will have a different weight, even though our mass has not changed. We're still made out of the same amount of matter. So we can calculate weight. Weight depends on the mass of an object that we're weighing and the gravitational field it's in. Now, we talked about the fact that a force could be a contact force or a field force earlier. A contact force has to touch, right? You push on something and you exert a force on it. But a field force acts over a distance, and gravity is a field force. It acts through a distance. So we are on or near the surface of Earth for most of our life. Unless you have the chance to get in a space shuttle and fly into outer space, you will be limited to on or near the surface of the Earth. And Earth has a pretty strong gravitational field, and what it does is it exerts a pull of 9.8 newtons per kilogram. Okay? Earth's gravitational field is 9.8 newtons per kilogram. So because the Earth is here with all of its mass, anything around it, any mass around it is attracted towards it. And the more mass that something has, the stronger that is. So if we look at what that unit says, that's a comparative unit, right? It says for every kilogram of matter in this field, that object will experience 9.8 newtons of force. And what that means is we can use this to calculate weight. We can say that the weight on Earth of an object is given by its mass times the strength of the gravitational field. Alright, so this formula right here, weight equals mass times the strength of a gravitational field, is how we calculate weight in general. On Earth, G on Earth is equal to 9.8 newtons per kilogram. It exerts 9.8 newtons of force per kilogram of material. So if I take the mass times that, so if I take 9.8 newtons per kilogram times whatever mass I have, say like 5 kilograms, then these kilograms cancel those kilograms, and 5 times 9.8 equals 49 newtons. And so I can tell that that thing has a weight of 49 newtons because it has a mass of 5 kilograms and it's on Earth. If we go to a different planet or we go to the moon, then the value for G on that planet or moon changes and we'll get a different weight